Thank you for joining us for the latest installment of the Pain Institute podcast. We're joined by Dr. Robert Braun. He's the Rowlinson Professor of Mechanical Engineering at the Colorado School of Mines. He leads the Advanced Energy System Group, who focuses on the study and advancement of sustainable and alternative energy systems. Thanks for joining us, Professor.
It's great to be here. Thanks, Jordy.
So you were recently awarded $7.7 million in funding from the U.S. Department of Energy to develop and test a full-scale hybrid stationary power system. Could you give us some background and maybe explain what a hybrid approach is and why this is so exciting for natural gas power systems?
Sure. The award is really to develop a full-scale hybrid power generation system. The full scale here is around 125 kilowatts. And the vision is to have these modules of 125 kilowatt power blocks that could be easily added in parallel, stacking up to over a megawatt, depending on the kind of application desired. These hybrid systems integrate more than one type of power generation technology. That's part of their uniqueness. And the primary reason for that integration is to make use of waste heat or waste energy to increase the overall system electric efficiency. So in our power plant system, we make use of novel metal-supported low-temperature solid oxide fuel cell technology being developed by one of our partners. And this technology electrochemically converts the natural gas that is supplied to it directly at very high efficiency into DC electric power. Now, in a fuel cell device, a fraction of that fuel is always unused. And in our system, we send this unused fuel gas, which is a small fraction, but maybe 15 to 20% is unused. And we send this to a high efficiency internal combustion engine, which will burn that residual gas and generate shaft power. And this shaft power is quite important because it drives other balance of plant equipment that is needed to operate the system. And by making use of this residual gas and converting it to shaft power, we effectively get electric efficiencies when combined with our high efficiency fuel cell technology will exceed 70% from natural gas. And so that's one of the reasons it's so exciting for us is usually you see such hybrid system technology only reaching 50 to 60% efficiency. And an example would be the very large scale natural gas combined cycle, which takes your old school Rankine cycle steam power plants and integrates that with gas turbines. And together they have two shaft powers that make electricity in the end and achieve the high 50s, perhaps 60% efficiency. But they are very large, 400 megawatt or larger. We are beating that efficiency by 10 percentage points at scales which are 100 to 1,000 times smaller. And that's one of the reasons it's so exciting. You don't need the huge capital outlay from a large power plant. You can do this at what we would call the distributed energy scale. Commercial buildings, hotels, hospitals, supermarkets, big box retail like Costco and Target and so forth, as well as large emerging end-use applications like data centers.
That seems really amazing, and I especially like you were saying the size efficiency and that they can be stacked in parallel to even increase output. So this seems like a relatively large step forward, and you mentioned that it's partially due to new fuel cell technologies and material manufacturing. So fuel cells haven't got as much attention as other sustainable technologies such as wind turbines or solar panels, but they seem to really benefit from technical refinement. We had Neil Sullivan on the podcast a few weeks ago, and he also talked about it. Do you feel as though this will continue? Do you feel like fuel cells are going to be very strong in the future? And what are some of the next steps after you prove that it works at scale?
Yeah, it's a really good question. And many people are wondering the same. One of the challenges that's independent of fuel cells is the relatively cheap cost of energy. And I'm talking really about electrical energy, which is extremely valuable. It has a high, what we might call thermodynamic potential. It's one of the highest grades of energy you can get is electric energy, but it's very cheap. And so part of the challenge of continuing is really, I think it's a market-based question, less so on technology. Some have viewed fuel cells as kind of perpetually waiting in trying to emerge. But I think it's largely about the emerging energy systems at large and how that is evolving and what are the problems that need solutions to. And fuel cells continue to emerge as a solution to many different energy end use problems. These could be in transportation and fleet vehicles. It could be in heavy lifts like forklifts. It could be in the distributed energy resource space when integrating with renewables to address variable energy resource firming. And so the fuel cell industry in general continues to experience double-digit growth in many markets. And the market in distributed generation is easily greater than 100 billion. And so as we see a mix of renewables and base load dispatchable energy, such as fuel cell technologies, continue to be attractive solutions, we'll see things like microgrids emerge and municipal energy planning and expansion being done through microgrids and distributed energy resources. Additionally, both energy resilience and sustainability emphasis continues to increase as what we call problems that need solutions. And I think fuel cells will continue to emerge as an effective technology and enabler of these solutions, as well as a possible transition technology for more variable energy resource firming. And I think there's another important aspect here, and that's that these very same electrochemical technologies, such as fuel cells that are being developed, are actually potentially useful in making fuels. And so operating them in reverse for grid energy storage, for synthetic fuel production, such as hydrogen or synthetic natural gas or even liquid fuels. And so these technologies in either operating mode, I think are going to continue to get traction and emerge as significant energy conversion devices in the future.
No, that's fascinating. I didn't even consider that you could run them in reverse, and a lot of what you said about some of the limitations or some how fuel cells can have different applications, and that's kind of been a limiting factor, I think, for a lot of other renewable technologies. You know, a lot of people are very concerned about renewable integration, how that's going to work with different grids, and making sure that they can be applied to some of the same needs as existing fossil fuel-based technologies. And your point about having this be a much more flexible technology that can be applied to different needs, and also being involved with fossil fuels, but also being able to fit into different areas of focus, I think is something that not a lot of people have thought about with fuel cells. I didn't know that, and I'm very interested to learn more about it. Do you feel like there's any limitations with fuel cells? So I know you mentioned that it could be used for forklifts. We've been talking about stationary power. Is there a scope, do you think, that'll fit best with fuel cells in the future, or do you think that it's going to continue to evolve as our needs continue to evolve?
Yeah, it's a great question. I think the limitations have been primarily, what is the problem that needs to be solved in, let's say, electric power generation of the future, or the energy system at large in the future, in terms of our trajectory towards lower carbon or carbon neutral technologies. These high efficiency devices aren't dependent on fossil fuels. The term hydrogen and fuel cells often goes hand in hand. Many of the fuel cell technologies that actually have more of a mainstream attention or focus are the lower temperature technologies, such as proton exchange membrane fuel cells, which are the primarily viewed as compatible with a hydrogen economy, compatible with transportation vehicles. There's a big push now to get fuel cells into marine transport. And so a lot of marine and naval applications for whether it's the heavy shipping industry or whether it's things like cruise ships and so forth. Hydrogen and fuel cells are beginning to get just a significant amount of attention and increased focus. And that is tied to hydrogen. And the fuel cells we're working on are certainly compatible because of their higher temperature with all kinds of fuels, not just hydrogen. They are fuel agnostic. And what's interesting in the news lately is natural gas for some time in the recent times has been viewed as a potential transition fuel to a renewable energy future. But some still say, hey, we're still emitting CO2. Why don't we just skip natural gas in general? And so there are cities that have probably 10, 12, maybe even 20 cities in the US who are looking at banning natural gas. But there are many other renewable fuels such as biogas, landfill gas, hydrogen, renewably produced synthetic fuels that this technology is completely compatible with. And when you switch to these other fuels, what you find is they're often not as cheap as shale gas. I mean, what can be cheaper than shale gas, right? Or what could even be cheaper than oil, which is cheaper than bottled water, though considering all of the steps that is taken to transport it, refine it, and ship it and distribute it. And so these technologies then become even more important when the cost of fuel is higher, because then you want the high efficiency to meet the economic conditions and metrics needed for the technology to be successful. And so in our steps, we're very mindful of that. And so while we're building out this new hybrid system, which is aiming to achieve 70% electric efficiency at around $900 per kilowatt, the work we have in mind is aiming at developing all the second generation equipment, testing these fuel cell stacks in our lab at Mines, and building and integrating all of these components together and testing it on a microgrid with our partner, Colorado State. And then that technology will be transitioned hopefully into the marketplace through additional demonstrations and our commercialization partner. And our primary commercialization partner is Kohler Power Systems, which has been working for decades in the stationary engine marketplace as backup generators, but now in combined heat and power as well. And so they're a great partner for us, and we really have an eye at accelerating this deployment through the auspices of ARPA-E. And so that is an aspect in which not only will this system benefit, but some of the components that are being developed to be implemented into this system are valuable in and of themselves. So for example, this equipment and this system that will be developed is going to put forth a new ultra high efficiency, ultra low cost inverter technology. And for those not familiar with inverters, this is a technology that conditions DC power generated by the fuel cell in a manner very similar to the DC power that's generated by solar PV panels. And the engine also will generate DC power. And this inverter will take that DC power and generate 60 hertz, 480 volt AC, which is suitable for end use applications and for the electric grid. And what's interesting about this is it's going to do so at costs that are at least 50% cheaper than you see now, and at efficiencies that are greater than 98%. So a lot of interesting aspects to what's happening around this system development.
It seems incredibly dynamic. You know, I wish I knew more about fuel cells, and it seems like this is definitely the future and able to solve all these problems that people bring up with renewable technologies. And like you were saying, you know, you don't have to necessarily use natural gas, and there's different aspects of this technology are applicable to different energy needs, which is, I think, exactly what we need with the future. You know, a lot of the future renewable technologies are very material intensive, and it's going to be complex sourcing and getting everything set up. And it seems like fuel cells are even a bridge in themselves to other renewable technologies. As a final question, do you have any final thoughts or anything else you'd like to share with the listeners? And also, I was wondering if you had any views on what you think the future energy landscape might look like, and including fuel cells. So if you had to envision a world 50 years from now, 30 years from now, do you feel like what role will fuel cells play? What role will fossil fuels play? Just as a guess, nobody's going to hold you to it.
Yeah, the crystal ball question. You know, it's interesting the way things are playing out because renewables continue to just experience a tremendous amount of growth and penetration. And there is a view in the future that electrons are maybe cheap, much cheaper than they are now. And that means electricity could see costs or prices, I should say, that in some time periods may be negative, meaning people will pay you to take the electricity. Although I think most don't really want to base a business venture on the idea that they will have significant amounts of free or even negative electricity costs. But it does appear that there will be some instances of that. But minimally, it does appear that there's the potential for low prices of electricity in the 1 to 2 cents per kilowatt hour range. And when that happens, now you have this interesting feature of, well, if I'm going to make electricity with fuel cells, now that could become a low value commodity. And that can make the picture for them more difficult if that future is what holds. I'm of the belief that there's going to be a lot of time of day, time of year pricing changes. And what's interesting about fuel cells, as I was saying before, is they can be run backwards as electrolytic or electrolysis devices, which make hydrogen, which make fuel, which allows one to take this excess electricity, could be at night from wind power, and to generate a fuel, which you can then dump into tanks, underground caverns, or into natural gas or hydrogen pipelines. And so now what you're seeing is an electrochemical technology which is suddenly interconnected and serving as a transition or an interface point between multiple energy infrastructures such as the electric grid and natural gas or hydrogen pipelines, and possibly seamlessly. And this allows you another dial to make the economics work in that you could, when the price of electricity is cheap, make fuel and run the system backwards and make power when the price of electricity is more valuable. In fact, this is a way in which, for example, the value proposition is being established for things like concentrated solar power plants where they collect excess thermal energy when you have lots of sun and the prices of electricity might be low. And then they dispatch that energy storage and make electric power for expensive nighttime electricity. And that makes their value proposition possible. And makes their so-called power purchase agreement prices that they would have to charge to be economic much lower. You could do the same with this technology, except you don't have to do it at 200 megawatt scale. You could do this at 100 kilowatt scale. So I think it's going to play a role. I think it's exciting. And furthermore, one of the things we didn't talk so much about is carbon. And carbon exists in the atmosphere, in the environment. And what are we going to do with carbon capture? We can electrify a lot of the energy system, but you still have past emissions to deal with, and you still have things like difficult to decarbonize industries like cement and steel industries. And fuel cells and electrolysis technologies can play a big role. And one of the primary reasons, for example, is that unlike an internal combustion engine device, whether it's a large gas turbine, whether it's an internal combustion engine and so forth that make power, those things mix fuel and air. With a fuel cell, they can keep these things separate. And because they make CO2 at much higher purity, that allows CO2 capture and separation to be done much more easily with fuel cell technology than virtually any other technology that generates power than I can think of. And so I just think there's a host of possible plays for this electrochemical technology, one of which is what we're developing. So I think the future is bright, though still shifting and evolving.
Thank you. No, that makes a lot of sense. And I I completely agree, and I think this is very insightful and very informative. I wasn't so aware that fuel cells had a broad scope, and I really appreciate you taking the time to talk to us today. And thank you for your time.
Absolutely.